Good evening, everyone. Thank you for joining in. I'm sorry for the few connectivity and people issues that we have faced. I'll start on the topic, the universe. So I was giving you a brief idea of what we'll discuss in today's webinar. So first we'll start with the few characteristics of the universe. We'll define what we mean by the universe and what is the observable universe. After that, we'll have a discussion on the Big Bang model. Big Bang model is a theory that we use to define the phenomena that explains the birth of the universe. After that, we'll do a short discussion on the death of the universe and how it's possible and what would happen when the universe will die. And what do we mean by the universe's death? Because actually, according to current science, the universe cannot actually explode or something can happen. We'll define death as the point where no activity is there in the universe. Everything is stationary. Spoiler alert, it's just a cold, dark ending. So, first we'll start with the basic rules that we use to define when we use the term the universe. The first rule is the most basic one. When we say the universe, we mean the observable universe. So, as I was telling you before, the light takes a finite time to reach places. The speed of the light is not infinite. All right, just a second. The speed of the light is not infinite. It takes a finite amount of time to reach places. So, when you're looking at the image of any celestial object, any celestial body, you're looking at this image in the past. So, when you're looking at a star, say the star is about 100 light years away from you. So you're looking at its image, which was 100 years in the past, because light from the star took 100 years to reach you. So now the star may be dead, or something might have happened to the star. A black hole could have eaten it, or it might have changed positions, or it might have collided with another star, or it might have ended its lifetime. So it might be dead by now, but you're seeing its image as it was 100 years in the future, and if it was dead by now, it will take you 100 years more to realize that. So looking through space is just like peering back in time. All right, so that's what I was saying. With this, we can say that, after a boundary, the actual universe does not have any boundary, but the observable universe does have one. So after a specific boundary, beyond a certain distance, galaxies disappear and the stars twinkle out, and no signals from the distant universe can reach us. So whatever there is after that boundary has not reached us right now. So there's a limit to what we can see. And as the universe is expanding, that boundary just goes away and away from us. So there are some parts of the universe that we'll never ever know about or never ever reach. So there's a certain limit to what we call the observable universe. This makes sense in the context that the universe had a beginning, a birthday, because everything is moving away from us. So it makes sense that everything was just at the same point. All right. So and that birthday is what we call the Big Bang. For a galaxy that's relatively close by, it's about the same age as we are. So this is a bit of a tricky part. So the galaxies that we see, the nearer galaxies to us, like the Andromeda galaxy or the galaxies in our local neighborhood, uh, feel that the universe is 13.8 billion years ago. They were formed around the same time. So their light reaches us at a constant, at a reasonable amount of time gap, so we can see the future, the nearly present image of the galaxies. So imagine a few galaxies that are very, very far away from us. They were formed just at the beginning of the universe. All right. So universe was say about it's right now about 13.8 billion years old. So at that time, the universe was about 2 billion years old. So we'll see that image of the galaxy to be shorter. All right. So we are seeing actually its past image. So at that time, galaxies would be smaller as compared to right now. They take time to grow and grow. So uh, at those galaxies which are really, really far away from us would be smaller. Right. Because I said that peering through space is just like peering through time. If we see a galaxy, I'll try to explain it a bit deeper, like in a easier way. Right. So imagine a galaxy that was born about when the universe was about 2 billion years old. So the light from that galaxy takes a huge time to come to us. So what we are seeing of that galaxy is that image in the past, because light has taken a finite amount of time, just like a star. We are seeing a star that is really, really far away from us, so we see its past image. So this is what the same thing that happens with the galaxy that is really, really far away from the Earth. So as you look further and further away, the galaxies would get smaller and smaller, because we'll be looking at back in, we'll look more back in time. So say that you look further even further than the galaxy. Right. So after that galaxy, you look more 100 billion light years into the space, and you'll find even smaller galaxies. So as you look further and further and further distance from the universe, you'll see that things are getting smaller and smaller because it's their past images. So the further you see that, you'll find smaller and smaller galaxies. I'll try to explain this with a brief simulation. Just a second, I'll have to change screens. Yeah. As you can see in this image, you'll find that galaxies that are closer on the scale are comparatively bigger and brighter. And as we move further and further away, the galaxies keep on getting smaller. As I explained it before, this is due to the fact that we are looking back to their past images. You can use this mnemonic like looking further and further in space is like looking further and further back in time. You will find that galaxies keep on getting smaller and smaller because they are the past images. So there will be images that will be about the time when they were born. So when they were born, they were really, really small. So we'll see them as smaller and smaller. As we look further and further away, we'll find galaxies getting smaller and smaller. If we look even further away, we'll find the first stars that were formed at the time of the universe. If we look even further away, we'll find a time when there were no stars. There was just matter lying around in the form of protons and neutrons. If you look even further away, you'll find the time of the antimatter versus matter war. So there was a time when there are two types of matter, two types of things to be precise, matter and antimatter. So if they come into contact of each other, they destroy each other. Alright. So if you have an atom of matter and an atom of antimatter, if they come close to each other, they destroy both of them and they release energy. So at the time of the antimatter versus matter war, say 100 billion particles of antimatter collided with 100 billion and one particle of antimatter. So the 100 billion and one particle of matter. So at the time, matter won the war against antimatter, and now it dominates. There is practically no antimatter right now, and there's just matter. So it's the scientific part of the discussion. It's not really necessary, but to prove my point, I'm saying that you look even further away from the further into the past when there was the antimatter and matter war. If you look even further away, you'll find time. At that time, there were no protons, no neutrons, no electrons. There was just everything was just ionized plasma. Even further back, you'll find all the subatomic particles that make up the universe. So when I say subatomic particles, I don't mean neutrons, protons, and electrons. I mean even smaller particles that make up neutrons, protons, and electrons, quarks, gluons, and so many particles that make up the universe as we know now. Even the unstable particles would be present there because the universe was very, very hot in the beginning, as we'll discuss when we discuss the Big Bang model. So you'll even find non-existent subatomic particles which are very, very unstable at in current conditions, but they could have been formed at that time. So looking back through space, looking into through space is just like peering back through time. I, I'll share, change screens again. Yeah. So this leads us to another point. The universe is the only constant. In each direction you look, you will see the same story. So the universe has that time to grow old in the same direction, in the same way. So if you look in this direction, you will see the same beginning of the universe as you'll see in this direction. So this makes sense. This shows us that the universe started as a point, because a point, as it started as a point, we'll see the same story unfolding in the same way. Right? If you see in this direction and you peer 13.8 billion years into the past, right? Like you peer very, very far away, so you'll see ionized plasma and everything that I said, all the same things. If you peer in this direction, you'll see the same things. You'll see the same story unfolding. There was the same beginning. So that beginning is what we call the Big Bang model. I explained everything that you could see the antimatter particles, matter particles, even before ionized plasma, and then even before that there was just quarks, gluons, and other subatomic particles that make up the electrons, neutrons, and protons. So with that we can discuss the Big Bang model. The universe has no boundary as per our definition. In space, we're saying that the universe has no boundaries. So there's no spatial boundary into the universe, but there's a boundary in time. We call that boundary the Big Bang. So the Big Bang was the birthday of the universe, as we just said. I should also add that it was a pretty hot day. So at that time, the temperature was about of the universe was about 10 billion degrees Fahrenheit, or about 5.5 billion degrees Celsius. So it was a really really hot time, and because of that all just a second, because of that heat energy, all the matter and energy were practically equivalent. So Einstein's equation E is equal to mc square suggests that matter and energy are practically the same interconvertible things. So if you have matter, you can make energy, and if you have energy, you can make matter. That's something that powers the stars and the whole universe as we know now. So at that time, matter and energy weren't practically equivalent, but they were the same thing. Right. So if you see energy, if you see matter, there now different things like energy powers houses. The house is mass, so that mass is matter. All right. So matter and energy are interconvertible, but they're not the same thing right now. But at the time, the temperature was so hot that matter and energy were practically equivalent. All right. So that time was called as the Big Bang. So universe started as a small point, and then it expanded into the universe as we know now. According to the standard Big Bang model, the universe was born during a period of inflation. Inflation means expanding. So it was born during a period of inflation that began about 13.8 billion years ago. Like a rapidly expanding balloon, it swelled from a size smaller than an electron to its nearly current size within the tiny fraction of a second. So uh, this point shows that the universe as we know it now is really really big. But at the beginning, it was really really small. Like it was even smaller than an electron, even smaller than anything you can imagine. So it was just all the mass of the universe was concentrated in a single point. And after the Big Bang, the universe started expanding. Initially, the expansion was really, really fast. So it expanded to just about its current size in a very, very few, in just a fraction of a second. So it's currently expanding right now also, but the expansion today is really, really slow than the expansion that was at the time of the Big Bang. Right. So yeah, it is the idea that the universe began as a single point and then expanded and stretched to grow as large as it is right now. So now what do we do? What do we mean when we say the universe is expanding? When we say that the universe is expanding, we mean that the expansion of the universe does not have any boundary, but if it had any boundary, it would be getting bigger and bigger. That's a layman way to explain what the universe is expanding. So I mean that the universe, the whole space, everything in space, the fabric of space time is expanding. It's not like it's expanding into something. It's not expanding into anything because the universe is everything that you know there is. So that fabric of space time is itself expanding. It's something difficult to wrap your head around. So it's the idea that the universe is expanding into itself. The space is itself expanding. So the space time that contains the galaxies, all the stars, our solar system, everything, that that space is expanding. So we can't yet explain what energy, what the force is behind that expansion and what powers the expansion. The universe is really really big, and the force that powers the expansion would be really really large, right? So that's what we mean by the universe is expanding. But it, the curious point here is that that expansion is accelerating, accelerated expansion. All right, so we call it accelerated expansion. So what do we mean by accelerated expansion? That expansion itself is accelerating. So I'll use a small story to illustrate my point. Say a car is running at a constant speed of 10 kilometers per hour. So that's what something we mean by the car. The car is moving, right? So we say that the car is moving, but say that the car is moving at 10 kilometers per hour now. After a few seconds, it's 20 kilometers per hour. Then after a few seconds, it's 40 kilometers per hour. Then after a few seconds, it's 80 kilometers per hour. So the speed of the car is accelerating. All right. So that's what we mean by accelerating universe. So at a point in time, so there are few confusing scenarios that you could get confused about. So there's one thing called as expanding universe. The other thing is accelerated expansion. So I'll explain first the wrong one, the wrong part of the theory. So if you say that the universe is just expanding, the expansion is not change it. So you'll see the universe to be say about, for example, 1,000 kilometers a day. The next day it would be 1,010 kilometers. Then even the next day it would be 1,020 kilometers. So the expansion is changing by 10 kilometers each day. But when we say accelerated expansion, so it would be the first day 1000 kilometers, the next day you'll see it as 1010 kilometers, and then the next day you'll see at 1050 kilometers, and then the expansion, the time gap between the 2 days will also increase. The space gap will also increase. So it's not just 10, 10, and 10 and 10. It would be 10, 20, 40, 80, and so on. That expansion itself is accelerating. So that's what we mean by accelerated expansion. It has been confirmed also by matlab, looking at galaxies, looking at stars that are at the end of space, that are really, really far away from us. They're moving at a very, very fast speed. So you see them at this much distance at a point in time. After a year or so, you'll see them at another distance. So you'll see them moving further and further away. So this also confirms the theory that I was telling you about in the beginning, that there will be a time that when we'll not be able to see any other galaxies or anything. So if this is the boundary of the universe, and after this we can't see anything. So as the universe is expanding, more and more things start to get away from this boundary. So somehow this galaxy was there, we can see this galaxy. It will take time to reach us, but we can still see that galaxy. But after a point in time, due to the expansion of the universe, that galaxy is moving further and further away from us. And after a point, it will cross that non-observable boundary, and it will be lost to us. So its light would reach us in the future, but we can't right now because of the time. But due to the expansion of the universe, it will cross that non-observable boundary and will not be able to reach us. So that's what the case. That's the case of accelerated expansion. We don't know what powers this expansion. Countless scientists are working right now on this theory. The theory is called as dark energy. So we believe that dark energy powers the expansion of the universe. All right, just a second. Yeah. All right. So I was talking about the force that powers the expansion. So we don't know what powers the expansion. There would be some really, really large force that's powering the expansion, that's causing the huge universe as a whole to expand. So we call that energy dark energy. We believe the dark energy is the energy of the matter, the space itself. So that space itself possesses the energy, and it's using that energy to expand. So that's called as dark energy. We haven't proven the existence of dark energy yet, but what we do know is that there is something, and there's a lot of it. All right. So this is all about the expansion of the universe. Uh, Now let's talk about the death of the universe. So according to our present laws, the universe will not itself die. What we're calling the death of the universe is a time when absolutely nothing is happening in the universe. There won't be anything interesting in the happen. There won't be anything interesting, or not even interesting, anything boring even to call it a universe. It will be a cold, dark ending. So the universe will be just a constant. So I won't be able to discuss all the events leading to the death of the universe because it's really, really far away from us. That's a really, really long time. It's so long that you can't even process that time limit. So, a spoiler to I should give a spoiler first. At the end of the universe, there will be just black holes, and we're calling the death of the universe when even the largest of the largest black holes, the most oldest one, die. All right. So black holes live practically immortal lives. But as we're discussing the death of the universe, we're looking at really, really huge time scales. So I'll rush you through that age of the universe in just a few minutes, but it'll actually take a really, really long time that we'll discuss further. Right. To give you an idea of such a time scale, we should know the end of everything. Only black holes will remain. So all the stars in the galaxy will die. There will be no star formation, and only black holes will be the places where anything else is happening. All right. So let's discuss what will happen until that time. So yeah, so we have stars and galaxies right now. All right, that those galaxies contain stars, and stars burn and they produce heat and light. The universe has light, visible light in it, and we can see things. So imagine a point in time that's really, really far away from us. So that point is very far away from us. But imagine that point when all the stars in the universe die. We discussed the death of a star in a previous webinar. So imagine the point when a star dies. So all the stars of the universe die. So there is star formation taking place, but after a time, even the star formation will stop because all the nebulas will be out of star material. There will be no star formation taking place after a time. The time would be far away from us, but no star formation will taking place at that time. So all the remaining stars in the universe are everything there is. So we say that all the stars have been dead by now, and there are only remnants of the death of a star. So after the death of a star, what remains is a black hole, or a white dwarf, or a magnetar, which we call a neutron star. All right. So that things are left out after the death of a star. So the universe will be a place full of neutron stars, black holes, white dwarfs, black dwarfs, which we'll discuss further. Those stars will be there. Now, at this point, we'll move even further in the timeline. Imagine that all the neutron stars are dead. They collided with themselves. They formed black holes, or they lived their lifetimes. All the neutron stars are dead. And what about the white dwarfs? The white dwarfs, after a period of time, just a second. Yeah, sorry about that. So after a particular time, the fuel of the white dwarfs will extinguish. So even the white dwarf would be dead by them. So they'll form black dwarfs. That's something we call black dwarf. There's just matter running through space. They don't have the heat and light of their own, which we use to define stars. So a star is anything that's luminescent, that has its own heat and light. Black dwarfs are just really cold, dark, empty, and not empty, cold, dark matter balls. All right. So after they are dead, and after all the neutron stars are dead, everything that's in the universe will be just black holes. So the black holes will be the only areas of any activity or any heat or light that's there in the universe. So if there is a civilization till that time, they'll be around black holes. So we'll have to choose a black hole and we'll have to orbit around that black hole to live for energy and anything. We discussed how to take energy from a black hole in our black holes webinar, where we use the rotational energy or any energy that the black hole gives to us, the heat energy, the light energy. We use the black hole's rotation to power electromagnetic waves to give us energy. So that's the point where I don't think any civilization, the human civilization, will be alive till that point. But if there's any other civilization that's going to live near a black hole, so we are at a point in universe when there are only black holes there. So black holes die in a process called as Hawking radiation. Hawking radiation is something that's really sciencey and we can't explain it right now. But it's the theory that small antimatter particles and matter virtual particles, which we call, they're formed near the surface of a black hole. Right. So this is the surface of a black hole, this line, and one particle will be formed here, and the other one will be formed there. So this particle would be sucked into the black hole, and this particle, its corresponding pair, would be out in space. So in the way that black hole has lost mass, those particles came from a mass. One of them got into the black hole, and the other one of the pair got back into the universe. So the black hole lost mass. You can imagine that this is a really really slow phenomena called as Hawking radiation, and black holes live practically infinite lives. So the time when a black hole, the time when the largest of the black holes in our universe will die is about 10 to the power 100 years. So that's 1 and 100 zeros after it. 10 to the power 100 years. So that time scale, these time scales are so huge that we can't even process it in lakhs, crores, trillions, millions. There'll be lakhs of trillions written here. So 10 to the power 100 years. Humans live a lifetime of about 80 to 100 years if you're lucky. So the black holes live a life of about 10 and 100 zeros after 1 and 100 zeros after it years. So that time is really really far away from us, but still we are discussing the death of the universe. So we imagine having a time machine with us and we are at the edge, edge of time. Right. So when the largest of the black holes, the oldest of the black holes, and the die, so that will be the time that will define the death of the universe. So there are no black holes, there are no neutron stars, there are no stars, no planets, no galaxies, no meat, nothing that can emit its light of its own. So the universe would be really a cold, dark, empty place. Right. So don't get depressed so soon. The ending is still a long way out. It is so far away that we can say that the universe has just been born. We still have a lot more planets, galaxies to visit, and a lot more secrets to unfold. We can't prevent the inevitable, but we can make the journey worthwhile. With that, we come to an end of the life of the universe and this webinar. What was before the Big Bang is a mystery. As we reach that point, as we go further and further back in time, we reach the point of the Big Bang. Near the point of the Big Bang, our science, our laws, as we know it, break down. The laws which we use to define the universe, all the science laws, everything breaks down as we know it. So our current phenomena, the theory of relativity, quantum mechanics, everything stops working. So we need a new theory to do maths around mathematical calculation or predict anything around the Big Bang. So still a mystery. Countless scientists are working on. It's called as quantum gravity. If you want to look for it, so at that point in time, our theories break down, and we don't know what happened at that time or what happened before it. We can only guess what might have happened. So there are a few possibilities that there might be an older universe which died to give us way, or it might be due to natural laws which we don't understand yet. The but what we do know is that we are all part of this huge universe, which has countless secrets hiding in its corners, some of which we never know, some of which we may never know. We are all made up of death stars, and death stars form the universe. Every year, the death stars that were before the solar system, they died to give way to new planets, and from the matter of these planets, the life as we know it emerged. So we are a way of the universe expressing itself. So with this, we come to an end of the webinar. I have a few intriguing questions for you to ponder upon. The most intriguing question for you is we'll discuss the most intriguing question at the end. I have a few questions like what if you say that the universe is all there is, then what is the universe expanding into? As we have discussed this question before, that it's not expanding into anything, the space itself is expanding. What was there before the Big Bang? How did the Big Bang even take place? Is there a complex phenomena that sparked the beginning of everything, or was it just natural? The most intriguing question for you to look upon is that the universe, we know that light speed is the cosmic speed limit. Light can move at about 3 into 10 to the power 8 meters per second. But the universe at its beginning was just about after a second, it was about 100 billion kilometers in diameter. So how did the universe grow into 100 billion kilometers when the speed of the light is just 3 lakh kilometers per second? So we have to imagine this. Like if you are traveling with the cosmic speed limit, that's the speed of light, you can only move 3 lakh kilometers in 1 second. But just in 1 second, the universe was about 10,000 crore kilometers. So 3 lakh is the speed limit, but the universe was about 10,000 crores in just the first second. Think about this for a while and research. Feel free to discuss ideas with me over the phone or WhatsApp or email. I'll put the email in the chat box if somebody does not have it. So this is the contact info. If you want to discuss any theories, anything, any doubts, anything, so you can discuss over the phone or email. I have put the details in the chat. I thank you all for joining, and I hope you all learned something new. Yeah, I thank you all for joining, and I hope you all something new. Do join me for the next webinar. Thank you, and have a great day.